Bismillahirrahmanirrahim. Assalamu alaikum. Dear students, welcome to the next class of CS131 Discrete Structures, where we'll be talking about chapter 11, which is about trees. So trees is a specific data structure that is very common to graphs. You can consider trees to be a special type of graphs with many different types of trees that are available. Some of them maybe you may already have heard of and you might be using as well in your basic programming and coding. However, I'll kind of take this course or take trees from the point of view of discrete structures, and I'll just be talking about them as a specific type of graphs. And so there are many topics that we're going to discuss in discrete structures, in particular in chapter 11, which is trees. Some of them are will basically be about basic introduction to trees, what trees are, what are rooted trees, what are unrooted trees, what is a node or a vertex, and how do you what are the restrictions of a trees, etc. Then we'll be talking about applications of trees in various domains of life, which will then be followed by tree traversal methods. So how do you traverse a particular tree? And then we'll be talking about spanning trees, a specific type of trees, and there we'll be talking about how do you perform tree traversal for spanning trees, which will finally be followed by minimum spanning trees, where we'll be focusing on Prim's algorithm and Kruskal's algorithm. So those are the topics that we have for chapter 11 for trees. So let's start off with the first section where we'll be introducing the concept of trees to you. Okay, so I just need to kind of talk about what really is a tree. So let's go to the PowerPoint slides which are here now on this, which you can probably see on the screen now, and let us discuss what trees are. So this is chapter 11 of your course textbook, and I'll basically be going through the slides for chapter 11. So the first section is about introduction to trees, and in this particular section we'll be talking about what is a tree. A tree is a connected undirected graph with no simple circuits, right? So any graph that is undirected and is fully connected and it has no simple circuits in it is what we call a tree. So for example, this G1 is a tree because it is connected, it is undirected, and it has no simple circuits in it. Similarly, let's go to this one. This is G2 is also a tree, since again this is connected, undirected, and no simple circuits. This one, on the other hand, is not a tree because there exists at least one circuit here, E, D, A, B, E. That's a circuit here, and hence this is G3 is not a tree by that definition. And if we talk about G4, G4 is also not a tree because it is not connected. We can see that, for example, the vertices A and B are not connected, right? So since they're not connected, hence this is not a tree. On the other hand, what is a forest? A forest is an undirected graph with no simple circuits with disconnected components. So for example, this example that we saw before is an example of a forest. It is an undirected graph with no simple circuits, but it contains disconnected components. For example, it contains two components. G4 has two components. And let's suppose this is one graph. This one graph is a single graph. It has three connected components, right? Three different connected components, and no circuits as well. So hence this is a forest by the definition. So note that each of the connected components of a forest is basically a tree. So if you take a connected component of a forest, it is going to be a tree. So an undirected graph is a tree if and only if there is a unique simple path between any two of its vertices. So you pick up any two of the vertices of a tree, and it is always going to be result in a unique path, right? So unique simple path. And if that is true, then it is, and the undirected graph is a tree for sure. And since you're using if and else if, that means if and only if, this means that vice versa is also true. If it is a tree, then it has to have a unique path between any two of its vertices. A rooted tree is a tree in which one vertex has been designated as the root and every edge is directed away from the root. So now let's suppose that we're given a tree T, right? And if you take root A, you can take any one of these vertices as its root. And if you take any of its vertices as its root, the thing is that then it becomes a directed graph. So from A, you can move to B, C, or D in that direction, right? Since A is connected to B, C, and D. And from each, for example, from C, you can then move to E. From D, that's the last point. And from B, you can move to F and G in that direction. However, if you pick a different route, for example, if you pick C as your route, then you'll start from C. You've got two options, E and A, right? E is the last option. From A, you've got D as your last option, as well as B. From B, you have got F and G as your possible options. So with the routing, you can notice that with a different route, we get a different tree. And what we observe is that a rooted tree is basically a tree in which one vertex which can be selected or given has been designated as the root, and every other edge is directed away from the root. So the direction of each edge is away from the root. From an undirected graph, we're getting a directed graph by routing it. And in this particular routing, the direction of every other vertex is the direction of every edge is basically away from the root. So let's think about some properties of rooted trees. And by now, I'm believing that you would already have studied recursion in your theory classes. So this is another thing that can be used here. So the rooted trees can also be defined recursively. And by recursion, we basically mean that you define a subpart, and if you find solution to that, you can actually build up, you can use that solution, which is a copy of the original problem, but just a simpler one to get the solution for the actual problem. So we can always change an unrooted tree into a rooted tree by choosing any vertex as the root. This is what I said earlier. Note that different choices of the root produce different rooted trees. This is what I showed you in the previous example. So we usually draw a rooted tree with its root at the top of the graph. Typical drawing is that you draw the root at the top, unlike the typical trees where the root is at the bottom. But in computer science, all the trees are drawn with the root at the top and the rest of the branches to follow. The arrows indicating the directions of the edges in a rooted tree can be omitted because it's understood that they're always moving away from the root. So we usually omit the arrows because the choice of root determines the directions of the arrows. Whatever is the root will always, everything is always directed away from it. That's why we have the root at the top. And every edge is basically by default pointing downwards, right? So then let us go with some terminology for trees. The terminology for trees has botanical and genealogical origins. Botanical is basically something that has to do with botany, and botany is a branch of biology, as many of you may already know. And the terminology here has its origins from botany as well as genealogy. Genealogy is the the studies of order, as I know it. So it has a lot of its root in biology and basic botany. So suppose that T is a rooted tree, and that's why you have the root and rooted tree and those terminologies that are being used here. Suppose that T is a rooted tree. If V is a vertex in T other than the root, right? The parent of V, and remember this is true for all vertices in T except for the root itself, right? So the parent of V is the unique vertex U such that there is a directed edge from U to V. So the direct parent of V would be the unique vertex U such that there is a directed edge from U to V. So that is what we call parent of V. So parent of V is the immediate vertex that is behind or that is before or that is earlier than U, and it has a directed edge connecting U to V. So when U is the parent of V, V is called a child of U. If U is the parent of V, then V is called the child of U. Vertices with the same parents are called siblings. So this is something that is again very common in our world as well in botany. So vertices with the same parent, two different vertices, two unique vertices that share the same parent are called siblings. The ancestors of a vertex other than the root are the vertices in the path from the root to this vertex, excluding the vertex itself. So remember, the vertex itself is not in the ancestor. However, the root is in the ancestor. That is, all the parents of a vertex, the parents, and so on until the root is reached, including the root, are ancestors of the vertex. So that is the definition of ancestors of a vertex. So these, you can notice, parent of a vertex, child of a vertex, sibling of a vertex, ancestor of a vertex. These are very commonly used terms that you see. Then the descendants of a vertex V are those vertices that have V as an ancestor. Whoever has V as an ancestor is the descendant of a vertex V, right? So descendant is another term that also used in common genealogy of family background, etc. You have been using those terms quite a lot, and hence the descendants would also be in the same category: descendant, ancestor, sibling, child, parent, right? So terminology is kind of very common. A vertex of a rooted tree is called a leaf, and this is something that has the botanical origin now. So you call it a leaf, a root, right? So those terms are what come from uh, botany. And on the other hand, from genealogy, you have got parent, child, sibling, ancestor, and descendant, etc. So whoever has V as its possible ancestor, that set of, or those vertices are called descendants of V. And on the other hand, a vertex of a rooted tree is called a leaf if it has no children. If it does not have any children further, then that is what we call a leaf node. So vertices that have children are called internal vertices. So those vertices that do have a children are called internal vertices. The root is an internal vertex unless it is the only vertex in the graph. So root is also an internal vertex unless it is only vertex in the graph. If root is only vertex, then in that case it is called a leaf and not the internal vertex. So internal vertices are those vertices that have children, and leaves are those vertices that do not have any children. So that they are two opposite things. If A is a vertex in a tree, so let's suppose that A is a vertex in a tree, the subtree with A as its root is the subgraph of the tree consisting of A and its descendants and all edges incident to those descendants. So the subtree is basically going to consist of A at its root and the whole descendants, including A and all its descendants and all edges that are incident to these descendants. If you take that part, that is what we call a subtree, right? It is a subgraph. It is a portion of the graph that has A at its root. So let's suppose that in the rooted tree T with root A shown in the figure. So now we have got root A as shown in the figure. Find the parent of C. Okay. Find the parent of C. What is the parent of C? Parent of C is B. The children of G, G has got H, I, J as their children. The siblings of H, so siblings of H are I and J. All ancestors of E. All ancestors of E are basically C, B, and A. Those are the ancestors of E. All descendants of B. All descendants of B are basically C, D, and E. So those are all the descendants of B. All internal vertices are basically C, H, I, J, G, B, and A. So those are all the internal vertices. And sorry, I is not also the internal vertices. It's basically C, H, J, G, B, and A. And all leaves. So leaves are basically the ones that do not have any children. D, E, F, K, I, L, M. Those are all these. What is the subtree rooted at G? So subtree rooted at G is basically this whole portion. So this is the subtree that is rooted at G. So let's talk about emery and binary trees then. If the previous example is clear and the basic notation is clear to you, I'll then move on to the basic emery and binary tree definition. A rooted tree is called an emery tree if every internal vertex has more than m children. So if each of the internal vertex has more than m children, then the rooted tree is called an emery tree, right? So it must have at least m or more than m children, then it is called an emery tree. The tree is called a full emery tree if every internal vertex has exactly m children. And notice that we are only talking about every internal vertex here, because of course for root they don't have any children, but every internal vertex including the root must have more than m children to be an emery tree, and a full emery tree if it has exactly m children. So an emery tree with m is equal to 2 is what we call a binary tree, binary for 2 children. So an emery tree with m is equal to 2 is called a binary tree. And here is an example of a binary tree where each internal vertex has got 2 children, and we observe that this is rooted at this particular value, and hence this is a binary tree. And you could call it a full binary tree as well, because each internal vertex here, whether it is this one or this one or this one, the 3 internal vertices, all of them have 2 children further. So that's why it's a full binary tree. This one is not a binary tree because it may contain 3 kids, but it is a full 3-array tree. So 3-array because the value of m here is 3. Every child has every node has 3 children. So this is a or no children if it's a leaf. So every internal node has 3 children, and in that case, that's why this is a full 3-array tree. And this one is basically full 5-array tree, right? So because every node has 5 children, every internal node has 5 children except for the leaves, which of course have no children at all. And this one here is a binary tree, again because each children has 2 or more vertices. So this is a binary tree. So what are ordered rooted trees? An ordered rooted tree is a rooted tree where the children of each internal vertex are ordered. So each internal vertex, you order them in a particular manner. Ordered rooted trees are drawn so that the children of each internal vertex are shown in order from left to right. And you can draw them to show them in a particular left to right. Note that a representation of a rooted tree in the conventional way determines an ordering for its edges. So if you have a representation of a rooted tree in the conventional way, it will determine the ordering for its edges. And we'll see some examples. So in an ordered binary tree, usually which we just call as a binary tree, if an internal vertex has 2 children, the first child is called the left child and the second child is what we call the right child. So in a binary tree where you have got only two children, each internal node vertex has 2 children, the left child will always be called the left child, right? The first child will always be called the left child, and the right child, the second child will always be called the right child. So left and right. So the first one on this side is left, the second one on that side is right. So first child is left child and the second child is the right child. And we'll use that soon when we talk about traversal of trees and other properties. The tree rooted at the left child of a vertex is called the left subtree. So the tree that is rooted at the left child of a vertex is what we call the left subtree of this vertex, and the tree rooted at the right child of a vertex is called the right subtree of the vertex. So note that for some applications, every vertex of a binary tree other than the root is designated as a right or a left child of its parent. So we kind of designate each child as either the left or the right child, except for, of course, the root, which does not have any parent, and for which we cannot designate the left or the right side. And this is also done even for when some vertices have only one child. In that case, we call them the left subtree or left child. So for example, what are the left and right children of D in the binary tree T shown in figure? So if we have this tree T, what are the left and right children of D in the binary tree? So for D, we can basically have this one. What is the left and right children of D? Well, the idea here is that in this case, we don't have any children. So there are no children in left and right. There's no. What are the left and right subtrees of C? So the left subtree of C is basically D only, and the right subtree of C is basically E only. It contains only one vertex. And the order is that implied by the drawing. So this is ordered tree, right? So here, if you put D over here and E over here, that is going to matter. So you'll notice that, for example, in this case, a smaller alphabet always precedes a larger alphabet. So for example, in the same line, B, F, and G are there. B is smaller than F and F is smaller than G. In this line, C is less than H and H is less than I and I is less than J. Of course, we cannot change sometimes the order. For example, in this case, it was easy, but sometimes it might be possible. It might not be possible to change the order. And in that case, we basically follow the order that is given to us as input. So let's talk about some applications of trees. Trees are used as models in such diverse areas as computer science, chemistry, botany, and psychology. For example, representing isomers of a compound in saturated hydrocarbons in chemistry, you are using trees. If you're representing the structure of a large organization, maybe in psychology, if you're representing the hierarchy of a file system with its directories and files, etc., you might have seen that example in the computer science course, the fundamentals of computer science, and so on. So what are balanced emery trees? The level of a vertex V in a rooted tree is the length of the unique path from the root to this vertex. So the level of a vertex is nothing but basically the length of the unique path that you take from root to this particular vertex, that is what we call the level of a vertex. The level of the root itself is defined to be 0, of course, and then the height of a rooted tree is the maximum of the levels of vertices. So height of a rooted tree is basically if you take the maximum of all, if you basically define all the levels of each vertex and then take the one that is maximum, that is what we call the height of a rooted tree. So that is the height, while the level itself is the number of nodes that are between you and between the designated node and the root itself. So root is at 0, you start at 1, 2, 3, and so on. So you define the number of vertices that are between you and the root. That is the level of a vertex. In other words, the height of a rooted tree is the length of the longest path from the root to any vertex. So of course, you take the longest path from the root to the vertex, and whatever is the maximum or the longest one, that is the length of the that is the height of the rooted tree. So a rooted emery tree of height h is balanced. So we call a rooted emery tree of height h as balanced if all leaves are at levels h or h minus 1, but not less. So if all leaves are at level h or h minus 1, then the rooted emery tree of height h is called balanced tree, balanced rooted emery tree. Balanced rooted trees have the property that the subtrees at each vertex contain paths of approximately the same length. So all the subtrees that are going to be drawn from each vertex will contain paths of approximately the same length. So let's take some examples and let's see. So for example, is this a balanced rooted tree? This is not a balanced rooted tree, since you basically observe some vertices here. So for example, here, if I take A, the height of this tree is basically 0, 1, 2, 3, and 4. The height is 4. However, we observe that some of the vertices are at level 1, level 2, level 3, etc. Hence, basically, the maximum that if we had all the vertices that are leaf vertices at either this level or this level, then we could have said that this is a balanced emery tree. However, this is not a balanced rooted emery tree. Is this a balanced rooted emery tree? Well, the answer is yes, because all of the leaves are actually leaves are at either this level. So this is, if I call this 1, 2, 3, 4, and 5. So and actually this is even a mistake. This actually should start at 0, not at 1. So this is 0, 1, 2, right, 3, 4. Yeah. So now we notice that all of the height of this tree is basically 4, right? Sorry, 5. The height of this tree is 5, and all the leaves are situated at either level 4 or 3 in this particular case. So this is, in this case, we know that this is a balanced emery tree or balanced binary tree, if you want to call it. So this is a balanced binary tree. Is this a balanced binary tree? No, it is not, because the height again is 5. However, we note that some of the leaves are present at level 3 and level 2 and 3 and 4, and hence they are not balanced trees. Is this a balanced binary tree? Well, this is also a balanced binary tree. However, this is not a full binary tree, since there are some internal nodes that have got fewer than 2 children, but still this is a balanced binary tree, I should call it. This is not even binary, because there are some nodes that have got a single vertex, and that's at most it must have, at least it must have 2 vertices. Okay, let's then talk about some of the properties of trees. A tree with n vertices has n-1 edges. So if there are n vertices in a tree, then it must have n-1 edges. A full emery tree with I internal vertices contains n is equal to m multiplied by I. So m is basically coming from this emery. I is the number of internal vertices. And since this is a complete or full emery tree, then it must contain n is equal to mi plus 1, m multiplied by I plus 1 vertices in total. A full emery tree with n vertices has, and from this we can always get that a full emery tree with n vertices has I is equal to n-1 divided by m internal vertices, and L is equal to m-1 multiplied by n plus 1 divided by m leaves. I internal vertices has n is equal to mi plus 1 vertices, and L is equal to m-1 into I plus 1 leaves. L leaves has, so a full emery tree with L leaves has n is equal to m1 minus sorry, mi minus 1 divided by m minus 1 vertices, and I is equal to L minus 1 divided by m minus 1 internal vertices. So these are just of some of the equations that we get if you can identify with n is equal to mi plus 1, then this is the automatic result of getting n, I, and L from this particular equation, right? So there are at most m raised to power h leaves in an emery tree of height h. So if there's an emery tree of height h, then there are at most m raised to power h leaves. So if an emery tree of height h has L leaves, then h is greater than or equal to log base m of L, right? The maximum height that you can get is basically greater than or equal to log m of L if the number of leaves, right? So if the emery tree is full and balanced, then h is equal to log to the base m of L, and you take the ceiling function of it. So we're using the ceiling function here. Recall that ceiling function of x is the smallest integer greater than or equal to x. So that brings an end to section 11.1. We'll not talk about section 11.2, and that is about the applications of trees. So I'll just continue on with this. So what are different applications of trees? Well, one of the simplest and straightforward application of trees is what we call the binary search trees. So searching for items in a list is one of the most important tasks that arises in computer science, and this we have seen in our previous lectures as well, where I was talking about searching techniques and stuff. So this is there. Our primary goal is to implement a searching algorithm that finds items efficiently when the items are totally ordered. So when the items are totally ordered, we'll want to find or implement a searching algorithm that can find items efficiently. This can be accomplished through the use of what we call a binary search tree, which is a binary tree in which each child of a vertex is designated as a right or left child. No vertex has more than one right child or left child, and each vertex is labeled with a key, which is one of the items. So for each vertex, you basically label them. We'll see in an example how this is done. Furthermore, vertices are assigned keys so that the key of a vertex is both larger than the key of all vertices in its left subtree and smaller than the keys of all vertices in its right subtree. So again, the concept of left subtree and right subtree here is very important. And based on that, you can basically assign vertices keys. With key, we know that everything in the right subtree is larger than this key, and everything in the left subtree is smaller than the key of the left subtree. So this recursive procedure is used. So by this way, we can actually label each vertex within a binary search tree, and this can then be used to form the binary search tree for a couple of items that we can define numerically. So we start with a tree containing just one vertex. We call it the root. The first item in the list is assigned the key of the root, right? So the first item is assigned as the key of the root. To add a new item, first compare it with the keys of vertices already in the tree. We're starting at the root and moving to the left if the item is less than the key of the respective vertex, if this vertex has a left child, or moving to the right if the item is greater than the key of the respective vertex, if this vertex has a right child as well. When the item is less than the respective vertex and this vertex has no left child, if it is less and it has no left child, then a new vertex with this item as its key is inserted as the new left child. Similarly, when the item is greater than the respective vertex and this vertex has no right child, then a new vertex with this item as its key is inserted as a new right child. So for example, we want to form a binary search tree for the words mathematics, physics, geography, zoology, meteorology, geology, psychology, and chemistry using the alphabetical order as a larger or smaller measure. So the first one we observe is mathematics. That is, since there is nothing present, so this is inserted as the root and the key to the first node. Then we insert a second alphabet, which in this case is physics. And we know that physics is larger than mathematics since P is larger than M. Hence, it will be inserted to the right. And we notice that there's no right children. So this will be made the right child with the name physics. Then we get geography, which is less than mathematics. And again, we notice that this tree has no left subchild. So we'll add a node here and name it geography. So this is now our current tree. The next value that we get is zoology. And zoology is basically greater than mathematics. So we move to the right side. It is greater than physics as well. We further move down, right? And here, since physics does not have a right child at all, so zoology is going to be inserted as the right child of physics. Then the next thing that we observe is meteorology. Meteorology is basically, now this is my current tree, and from this tree, meteorology is larger than mathematics, since ME is larger than MA. However, it is since this is larger than mathematics, we move in here. However, it is less than physics. Hence, this will be, and physics does not have a left child, so it will be inserted as a left child of physics. And this is exactly what is done for meteorology. Then the next thing we observe is geology. Geology is less than mathematics, but greater than geography, since L is greater than G. So it will be automatically be inserted as the right child of geography, and that is what is exactly done over here. Then the next thing we observe is psychology. Psychology is basically larger than mathematics, larger than physics, but smaller than zoology. So it will automatically go down, down, right side, since larger than mathematics, go to the right, larger than physics, go to the right, but smaller than zoology, so go to the left. And since it does not have a child here, so psychology will be inserted as the left child of zoology. Then chemistry. Chemistry is basically smaller than mathematics. It is smaller than geography. And since geography does not have any left child, so it will be inserted as a left child of geography. So what we know now is that we have now formed a search tree where for all courses or for all the specific subjects. And if you want to search in this particular tree, the search is much easier, because all you have to do is you have to go into the right into the correct plane of it. For example, if I want to find chemistry, I can just compare C with M, smaller, so move to the left side. C is smaller than G, move to the left side. And here I can find chemistry right away, right? On the other hand, if I want to find, for let's say, for example, geology, then G is less than M, move to the left side. G is greater than geography, so now move to the right side. And on the right, I can actually find geology. And if something is absent, I can even find that. So for example, if you want to find biology in this, the answer would be biology is less than mathematics, so go to this side, left side. Biology is less than geography, go to the left side. Biology is less than chemistry, go to the left side. But here again, we cannot find any child, and hence we can, when I reach chemistry, I can actually be confident here that since it does not have any child, hence biology does not exist in my particular search tree. So this is a very important application of binary search tree, and this is what we see over here. I'm not going to go into the algorithm here. It's kind of too complex for you at the moment. However, I can maybe just try, and since you know a bit of programming, I'll just try to go through it. So let's suppose that you want to insert. This is for how you are going to locate an item in or add an item to a binary search tree. So if you want to add an item, what you need is the X, the item, and basically T, the binary search tree. And we can actually search for it. If it exists there, we'll kind of give it back. If it does not exist, we'll then add it in. So for example, if root of T, if we know that the item does not exist, then we'll add it as a new vertex. Otherwise, if it already exists, then we don't need to add it in. We just need to return the searched algorithm. Anyway, I'm not going to go into detail of this particular algorithm now, although this is too simple for you to understand with programming. Let's take another example. Use the algorithm 1 to insert the word oceanography into the binary search tree. And if you have to insert the word oceanography, for example, in this search tree, the answer is again simple. You match and move on and insert it at the correct place where you identify it, right? So the rooted trees can be used to model problems in which a series of decisions leads to a solution. And that is what we call a decision trees, right? So the rooted trees can be used as decision trees as well. For instance, a binary search tree can be used to locate items based on a series of comparisons, like I just did before for biology or something, where each comparison tells us whether we have located the item or whether we should go right or left in a particular subtree, like I did before. A rooted tree in which each internal vertex corresponds to a decision. Right, each vertex leads to a particular decision with the subtree at these vertices for each possible outcome of the decision is what we call a decision tree, right? So the possible solutions of the problem correspond to the paths to the leaves from this rooted tree. So the paths to the leaves from this rooted tree and are basically the possible solutions of the problem. So let's take another example. Suppose there are 7 coins, all with the same weight, and a counterfeit coin that weighs less than the others. So there's a coin that weighs less than the others. How many weighings are necessary using a balance scale to determine which of the 8 coins in the count is the counterfeit one? Give an algorithm for finding this counterfeit coin. So the idea here is that there's a coin which weighs less and you need to find that out. And the idea is really simple. All you need to do is you have got 8 coins, one with the counterfeit one. One way of doing it, I think the solution that you are going to come up with is that, pick up 2 coins and pick up the first 2 ones, weigh them out, right? If one is less than the other, we can basically say that since if they're equal, they're both we can discard them. However, if one is less than the other, we can simply say that this one is basically the one with the lower weight. The other way would be that you just weigh them once, weigh 2 coins together, one on one side, the one on the other side, and if they're equal, we discard both of them. Pick up the second ones, again weigh them, and in this way 4 weighings are necessary till you find basically the coin. We are sure to find a coin in this particular scenario, taking 2 at a time and removing both or removing we might be able to find it even earlier, but at least at most 4 weighings will be needed. Another way could be, and that's a slightly different algorithm if I'm going to give it, is to put 4 coins together and put the other 4 coins together. One of the pans will weigh less than the other, and in that case we discard the ones that weighed equally, but the ones that weighed together, we again divide them into 2 and 2 again. So 2 coins in one and 2 in the other. One of them will again weigh less, and this one again discard the other 2 and just keep these 2, and you just need to make one more weighing before you are able to come up with the coin that has lesser weight. And in this case, if you notice, we just made 3 weighings, first with 4 coins, then with 2 coins, first with 8 coins, right, divided into 4 and 4, then with 4 coins divided into 2 into 2, and finally with 2 coins divided into 1 by 1. And in this case, this is a quicker or a faster way. We got our answer in just 3 weighings. And if you notice, if we had 16 coins, we would have needed just 4 different weighings in this particular scenario. And if you had 32, we'd only require maybe 5 different weighings. So an increase here is not, an increase by 2 actually is not increasing the. If we double the number of coins at each step, we are not actually doubling the searches, but actually we're going really slow. We're going by the logarithm to the base 2 of it. And this is possible because the algorithm that we are using in the second case, in the first case, if you take 2 coins, you're actually going to require 16 different comparisons in the worst case. For 32 coins, for 16 coins, you would require 8 different comparisons. For 4 coins, you required 2 different comparisons, and so on. So log to the base 2 is much faster and much better, and that is exactly the thing that we're going to use here. There are 3 possibilities for each wing on a balance scale. The 2 pans can have equal weight, the first pan can be heavier, or the second pan can be heavier. Consequently, the decision tree for the sequence of wings is a 3-array tree. You have got 3 options at each step. There are at least 8 leaves in the decision tree because there are 8 possible outcomes, right? So that we can again identify, because each of the 8 coins can be counterfeit lighter coin, and each possible outcome must be represented by at least 1 leaf. The largest number of weighings needed to determine the counterfeit coin is the height of the decision tree. So whatever is the height, if you take 2 and compare them, that is basically the height of your decision tree. In that case, it's going to be 4. Otherwise, in the other case, it's going to be 2. The height of the decision tree is at least ceiling log 3 to the power 8, which is 2. So the height of the tree is basically 0, 1, and 2. That's the height. Hence, at least 2 weighings are needed. So at least 2 weighings are needed. It is possible to determine the counterfeit coin using 2 weightings. And the decision tree that illustrates how this is done is shown in figure, and we'll see the figure here. Suppose that there are 7 coins all with, and this is the question actually. So we notice that you can actually put 3 coins and 3 coins on the balance. If they weigh equal, all you need to, this is the next level, and this is actually even faster than the one that I had decided or that I had fixed myself on. So in this case, this is what they do. They pick up they pick up 3 coins, the first 3 coins and the second 3 coins. Remember that the last 2 coins are still not matched, the 7th and 8th one. And what they do is they put them on the two pans, so 3 here and 3 here. And there can be 3 outcomes. One is that 1, 2, 3 is lighter, right? The other is that they are balanced. And finally, the third one is that 4, 5, 6 is the lighter one. So let's take the first outcome, in which the lighter one, in this 1, 2, 3 is lighter. In that case, all you need to do is you need to check for 1 and 2 again now. And 3 is by default out there. So now the answer is, if 1 is lighter, then 1 is the counterfeit coin. If 2 is lighter, then 2 is the counterfeit coin. But if they're balanced, then it is the 3, which is the lighter coin. Again, just 2 comparisons and we're done. So this is the height of efficiency here. I would have done it in 3 steps. He's doing it in 2, so even better. Let's take the second scenario where both of them are balanced. If both of them are balanced, we know that neither of these coins is a counterfeit coin. And all you need to do is check for 7 or 8. And we know that for 7 and 8, there are only 2 possible outcomes. Either 7 is lighter or 8 is lighter. They cannot be balanced. This is an impossible statement. Hence, if 7 is lighter, this is a counterfeit coin. If 8 is lighter, this is the counterfeit coin. On the other hand, we can do the similar thing for 4, 5, and 6. We know that since this is the lighter side, we can maybe compare 4 and 5. If 4 is lighter, then 4 is the counterfeit coin. If 5 is lighter, then 5 is the counterfeit coin. If they're balanced, then it is 6, which is the output here. Again, in 2 steps, in 2 wings. And this is done because you have converted into a 3-array tree and not a 2-array tree like I was doing. So if you convert it into a 3-array tree, so log 3, log of 8 to the base 3 is 2, and then you take the ceiling function of it, and it is 2. So those are the number of weightings that are needed to identify or to determine the counterfeit coins using 2 weightings. That's it. So let's take another example. Decision tree for sorting 3 distinct elements. If you're given 3 distinct elements, you can basically again use a distinct sorting tree to actually you can use a decision tree to sort 3 distinct elements. So for example, we can have A and B compared first. If A is greater than B, you move to the left side. If A is less than B, you move to the right side. Then if B is, then you compare B and C. If B is also less than C, then you basically get C is greater than B is greater than A, right? Otherwise, you move to the corresponding other path, which is B is greater than C. In this case, again, you compare A and C with themselves. If A is greater than C, then B is greater than A is greater than C. If A is less than C, then basically B is greater than C is greater than A. And similarly, you can basically draw a decision tree for sorting 3 distinct elements, again, just by traversing through the tree, making the right comparisons and coming up with the corresponding solutions. And we know that there are basically 6 different possibilities if you compare A, B, and C. And all of these are represented as leaves in this particular decision tree. So then there are some certain theorems that are very important for searching in a tree. And I'm not going to go through them because maybe the first line, since we have not covered the complexity. So a sorting algorithm based on binary comparisons requires at least log to the base 2 n factorial different comparisons. And that was what we did earlier when I made a binary algorithm and binary tree based algorithm. So the number of comparisons used by a sorting algorithm to sort n elements based on binary comparisons is big omega of n log n. What big omega is, we may discuss later, or if you know that, then it's absolutely fine. The average number of comparisons used by a sorting algorithm to sort n elements based on binary comparisons is again big omega of n log n. So another very important application is what we call the prefix codes. And what is a prefix code? Well, consider the problem of using bit strings to encode the letters of the English alphabet, where no distinction is made between lowercase and uppercase letters, right? So the uppercase letters and the lowercase letters do not have any distinction. And we want to use bit strings to encode the letters of an English. We can represent each letter with a bit string of length 5, since there are only 26 letters and there are 32 bit strings of length 5. So we can use bit strings of length 5 to encode them, right? To put the to represent each letter. We can use 5 bit strings. We can use a bit string of length 5. The total number of bits used to encode data is 5 times the number of characters in the text when each character is encoded with 5 bits. Of course, if you put each character as 5 different bits, then the total number of bits used will be 5 times the number of characters. Is it possible to find a coding scheme of these letters such that when data are coded, fewer bits are used? Can we use fewer bits? And yeah, if you can, you can always save memory and reduce transmittal time if you can somehow reduce the size of the uh, bit string. So consider using bit strings of different lengths to encode letter. Can we use different bit strings of different lengths to encode letter? Well, letters that occur more frequently should be encoded using short bit strings, and longer bit strings should be used to encode rarely occurring letters. And this is something that you have already seen actually in the cryptography part, chapter 4, section 4.6. The cryptography you have already used something similar for encryption and decryption. So we can use more frequently, we can represent them using shorter strings and using longer bit strings for rarely occurring letters. When letters are encoded using varying number of bits, some method must be used to determine where the bits for each character start and end. Of course, when letters are encoded using varying number of bits, then some method must be used to determine where the bits for each character start and end. For instance, if C were encoded with 0, A with 1, and T with 0, 1, then of course we cannot differentiate if it's if it's an EA, right, or it is T for bit string 0, 1, 0, 1. So it can correspond to multiple things, and hence we will not be able to differentiate. So it is necessary that some method is for encoding and decoding is very clearly mentioned. So one way to ensure that no bit string corresponds to more than one sequence of letters is to encode letters so that the bit string for a letter never occurs as the first part of the bit string for another letter. So it's never the prefix of another letter. And codes that actually follow this particular property are what we call prefix codes. That is, a prefix is always unique to a string, and that prefix can never occur for another letter. For instance, the encoding of E as 0, A as 1, 0, and T as 1, 1 is a prefix code. Since for these three letters, however you try to encode them, it will always be a unique coding, right? We'll know by reading the letter 0 first, or wherever a single 0 occurs, we'll know that it is an E. Wherever a 1, 0 occurs, we now know this is an A, and wherever 1, 1 occurs is a T. And a word can be recovered from the unique bit string that encodes its letters. For example, the string 10110 is the encoding of ATE. 10 for A, right? Single 1, double 1 for T, and a single 0 for E. To see this, note that the initial one does not represent a character. So initial one does not want a character, but 10 does represent A, and could not be the first part of the bit string of another letter. So again, 1 cannot be the first part of any bit string of another letter. Then the next one does not represent a character, but 1, 1 does represent T. Again, 1 is not a character, but 1, 1 does, and that's T. And the final bit 0 does represent a character, which is E. A prefix code can be represented using a binary tree, where the characters are the labels of the leaves in the tree. So this is where prefix codes and trees or binary tree come together. So a prefix code can be represented using a binary tree, where the characters are the labels of the leaves in the tree. So you can basically label each leaf as possibly the character. The edges of the tree are labeled so that an edge leading to a left child is assigned a 0, and an edge leading to a right child is assigned a 1. The bit string used to encode a character is the sequence of labels of the edges in the unique path from the root to the leaf that has this character as its possible label. So for example, in this case, we want to label E, A, T, and S. You can note that there is no encoding, there is no label given to the internal node, including root. However, if you have a first 0, then you get a leaf E. If you get a 1, it is an internal node, then the next 0 is an A. Similarly for T, similarly for N and S, where we now have got a prefix tree, in which E is represented by the encoding of 0, A by 1, 0, T by basically 1, 0, 0, 1, 1, 0, N by 1, 1, 1, 0, and S by 1, 1, 1, 1, right? And in this case, we are sure to, since E is the most occurring letter followed by maybe A and then by T. And yeah, so in this case, we are sure that we are going to, have a very small, we are going to save a lot of code. We are going to save a lot of space by encoding it using these prefix codes. Okay, so the tree representing a code can be used to decode a bit string. For instance, consider the word encoded by 5 ones, 0, 3 ones, 00 using the code in figure. This bit string can be decoded by starting at the root using the sequence of bits to form a path that stops when a leaf is reached. So whenever you leave for each, you're going to stop there. This bit string can be decoded by starting at the root using the sequence of bits to form a path that stops when a leaf is reached. So this is duplication here anyway. Each 0 bit takes the path down the edge leading to the left child of the last vertex in the path, and each 1 bit will correspond to the right child of this vertex. So 1 corresponds to the right child, 0 corresponds to the left child. Consequently, the initial 4-1 corresponds to the path starting at the root, going right 4 times and finally leading to a leaf in the graph that has S as its label, because the string 4-1 is the code for S. And you can go back and see that, if you go back 4 steps here, then you ultimately reach S. So S is the first letter. Continuing with the 5th bit. So now you start with the 5th bit. These first 4 bits are used. So now let's start with 1, 0. And 1, 0 we know is the code for A. So 1, 0 is the code for A. So it now becomes SA, right? And we have used 1, 0 again. So now we are left with 1110, and 1110 is the code for 1110 is the code for 1, 1, 1, and 0 is the code for N, right? So 1110 is the code for N. So again, you can use these 4, and now you have reached the point N. And finally, yes, so this is basically S, A, N. And finally, you have got 0. 0 is the code for E. So 0 is the code for E. So hence SANE is your basic word. And this is exactly the one that we are going to retrieve by using the bit string and using the prefix codes. So, but note that to get the correct word out, you not only need the encoded word, right? But you also need the prefix code as well. So you need this tree as well as, so you need to first pass this tree and then, give the bit string, and then you can always encode or decode it, whatever is required based on the tree. So we can construct a prefix code from any binary tree where the left edge at each internal vertex is labeled by 0 and the right edge of a 1, and where the leaves are labeled by characters. So you can actually do that easily, where each leaf is a character and each left internal vertex is labeled by a 0, and each right edge is labeled by a 1. So characters are encoded with the bit string constructed using the labels of the edges in the unique path from the root to the leaf. So you actually use the labels of the internal leaves and the edges to determine the unique path and that way. However, there's a specific algorithm which we call the Huffman coding, and that is a very interesting algorithm. Huffman coding is an algorithm that takes as input the frequencies, which are the probabilities of occurrences. You might have studied that, what a frequency is, or the probability of occurrences of symbols in a string, and produces as output a prefix code that encodes the string using the fewest possible bits among all possible binary prefix codes for these symbols. So it guarantees that it is going to produce it in the fewest possible bits. Note that this algorithm assumes we already know how many times each symbol occurs in the string. So it calculates the frequency of the occurrence of a symbol in the string, so that it can then compute the frequency of each symbol by dividing the number of times the symbol occurs by the length of the string. And Huffman encoding is a fundamental algorithm in data compression, the subject devoted to reducing the number of bits required to represent information. For example, you might be using the JPEG in your images, and again, this used to be one of the algorithms that was used for the JPEG encoding of images, and that was how the images were transformed into their corresponding into the bits and transferred for and that is so that is exactly what is mentioned here. Huffman encoding is extensively used to compress bit strings representing text, and it also plays an important role in compressing audio and image files, especially the JPEG files. So here's an algorithm for it. Again, I might not go into detail here, but I can just go through it for you. We'll see how to apply this actually, and that is the more important fundamental part. The procedure is for the named Huffman. As input, it takes symbols AI with their frequencies wi, where I is equal to 1 to n. So it takes all the symbols from 1 to n, and it knows the frequencies of each particular symbol. So F is a forest of n rooted trees, each consisting of single vertex AI and assigned weight wi. So initially you have got a forest of n rooted trees, where each is basically consisting of a single vertex AI. It only contains a single vertex, and it has assigned it the wi weight is assigned to that particular symbol. So while F is not a single tree, while the forest is not converted to a single tree, this is what we are going to do. We replace the rooted trees T and T bar of least weights from F with WT is greater than equal to WT bar with a tree, having a new root that has T as its left subtree and T bar as its right subtree. So you basically add a new node, new vertex, and T bar are the ones that have got the least weights. So you put them as left and right subtrees of basically this new tree. Label the new edge to T with a 0 and the new edge to T bar with a 1. So the left side is now 0, the right side is 1. That's a new tree with T as its possible root. Then we assign WT plus WT bar as the weight of the new tree. So the weight of the new tree is going to be WT, whatever was the weight of the left subtree and whatever is the weight of the right subtree. And you keep on doing it until basically you finally reach a single tree. And the Huffman encoding for the symbol AI is the concatenation of the labels. So the encoding for symbol AI would be the concatenation of the labels of the edges in the unique path from the root to the vertex AI. So let's, I think, see an example soon. So given symbols and their frequencies, our goal is to construct a rooted binary tree where the symbols are the labels of the leaves. The algorithm begins with a forest of trees, each consisting of one vertex, where each vertex has a symbol as its label and where the weight of this vertex equals the frequency of the symbol that is its label. At each step, we combine two trees having the least total weight into a single tree by introducing a new root and placing the tree with larger weight as its left subtree and the tree with smaller weight as its right subtree. Furthermore, we assign the sum of the weights of the two subtrees of this tree as the total weight of the tree. So you can basically put the sum of the two weights and that is going to be the total weight of the tree. Although procedures for breaking ties by choosing between trees with equal weights can be specified, we'll not specify such procedure here. If there's a tie, you don't need to specify that for now. The algorithm is finished when it has constructed a tree, that is when the forest is reduced to a single tree. And here is the basic thing, an example that displays this whole part. Use Huffman coding to encode the following symbols with the frequencies listed. So for example, A has a frequency of 0.08, B has a frequency of 0.1, C has a frequency of 0.12, D has a frequency of 0.15, E has a frequency of 0.2, and F has a frequency of 0.35. What is the average number of bits used to encode a character? So what is the average number of bits that is required to encode a character? Well, the idea here is that you like if you go step by step, I think so. This is the part from where we start, right? So this is my starting point. A has a frequency of 0.08. So this is now this is the initial forest. Each one of them is basically a standalone node with its weight assigned to it, right? And from this, you basically select the one that have got the least weight. The ones that have got the least weight as per this graph are basically 0.08 and 0.1, right? So others are larger. So this is the initial forest that I get. So A and B have the least weight. So the first idea is to combine A and B and get their weight summed up. In this case, A has got a weight label of 1 and B has got a label of 0. And 0.18, which is the sum of their weights, is put up as over here, right? So next, this is the first step. In step 2, we then identify from this particular forest now. Since this is not a single tree now, we need to continue with each step. In this case, the one with the lowest weight is basically C and D now, right? So this is larger. So C and D are combined together again by using 0, 1 as their possible labels, right? So this is now A and B is 0.18, E is 0.2, if you combine C and D together in this manner, it then becomes 0.27, and then we've got 0.35. So the ones in this step that I have the lowest weight are basically AB and E. So you need to combine them together again using the same label. So AB are combined together in this step. Once you combine AB together with E, you basically get the sum of 0.18 and 0.2, which is 0.38. 0.38 is larger than this. So you now have got 0.27, 0.35, and 0.38 in your possible trees. In this again, if you take this one as your lowest value, these two are going to be combined together and form up a value of 0.62, which is given here. Again, you see the labeling that is going on, 0, 1, 1, 0, 1, and so on. And finally, you need to combine these two together simply by assigning a 0 and 1 here. And this now comes up to be a value of 1 exactly. And 1 is the largest value. So now this is a single tree. And here we know that from this tree, if you have a 0, 0 that corresponds to F, if you have a 0, 1, 0 that corresponds to D, a 0, 1, 1 corresponds to C, a 1, 0 corresponds to E, a 1, 1, 0 corresponds to B, and 1, 1, 1 corresponds to A. And that is exactly the one that is mentioned for, I think, for all of these, right? And the question here is that now we know the encoding, right? So we know that A is encoded by 111, 110, 011, 010, 10 alone, and 00 alone, right? So we know this. So the average number of bits that are used to encode a symbol using this encoding is going to be basically 3 multiplied by, since there are 3 bits that are required for the first letter, which is A, and A has a frequency of 0.08. So 3 multiplied by 0.08. Then you require 3 alphabets for B. So 3 multiplied by 0.1 plus 3, then for C, you actually have got 3 again. So 3 multiplied by 0.12. And for D, you have got 3 again. So 3 multiplied by 0.15 plus 2 for basically 0.2, so 2 multiplied by 0.2, and then 2 for 0.35 as well, so 2 into 0.35. So this comes up to be 2.45. And we know that for the given frequencies listed, and for the, I think this is the minimum number of bits, minimum number of average bits that are going to be used, and we cannot go beyond that. Using any other algorithms. This kind of guarantees that. And that is a very important factor of this Huffman encoding. Notice that the question here that was asked is the average number of bits that are used to encode a character. So the first thing, of course, is that you find the corresponding Huffman encoding. And after you find the Huffman encoding, then you can know the number of bits that are used for each character. And then you just need to multiply them with the frequency that is mentioned. And if you multiply them with the frequency and get the sum, that is the average number of bits that are required for this particular message using this particular Huffman encoding. So that brings an end to section 10.2 as well, section 11.2 as well. So we have already discussed the introduction to trees, and we have discussed the applications of trees. In particular, we saw the Huffman encoding and the binary search trees, etc., as possible applications. In the next lecture, we'll start with the tree traversal and how a tree is traversed using tree traversal techniques. So with that, I'd like to wish you all the best, and I hope you've learned something about trees in this particular section and lecture. Thank you very much. Yeah, so that's about it. See you in the next lecture on traversal of trees.